Okay, so thank you. I apologize for not being here. I would have liked to come, but could not. So I hope you'll be able to hear me okay. And otherwise, just send me an email afterwards and I'll gladly answer any questions. So here's the outline of the talks. First, I will give some motivations for computing isogenies between abelian varieties. Of course, we are at an isogeny workshop, so I don't think you need much motivation. And I need to speak a bit about polarized abelian varieties. So polarization is something we don't worry too much with elliptic curve because there's only one of them. But suddenly, as soon as you go to higher dimension, you need to worry about polarization. So Ben will give a talk tomorrow going much more into details, but I'll need to explain a bit about polarization and the link between isogenies and polarization. So there'll be quite a few definitions. But then at the end, I will give you some generic outline for how algorithms for isogenies work. Before I begin, I'd like to advertise a postdoc position in Bordeaux. It's a 1-year postdoctoral position for anything related to isogeny-based cryptography. And the position is available until 2024. So it should end before April 2024, but we should be able to extend it by 6 months. So if you're defending your PhD this year or soonest, don't hesitate to apply. I did not advertise this position sooner because we were under COVID and so on, so it was not a convenient way to work, but now everything is back to normal and Bordeaux is a beautiful city. Okay, so let's first start by motivations. So there are a lot of usage of isogenies, like for number theory. They can be used to speed up the arithmetic, like speed the multiplication by 2 or 3 and gives faster arithmetic. They are used to determine endomorphism ring. If you look at the to know where we are in the volcano. They are of course used for point counting algorithms, be they L-adic or P-adic. The seed point counting algorithm, the Sato-Kedlaya point counting algorithm. So small publicity, my PhD student Kiefer has a C-like algorithm in log to the 4q, so the same complexity as for elliptic curve to count points for abelian surface with explicit RM. So isogenies are also used to compute class polynomials, modular polynomials. Somewhat surprisingly, they are used to speed up arithmetic for FQ, so not for elliptic curve, but directly for FQ. So isogenies between elliptic curve are used to find good irreducible polynomial for finite fields. So that's work by Couven and Lercier. And I also use isogenies with Ritz-Thaler to find curves with many points, to explore isogeny graph, for instance, find isogeny component with no Jacobians in dimension 4, because as you know, in general, in dimension 4, an abelian variety is not a Jacobian, but maybe it could be isogenous to a Jacobian, but we found some component where there are no Jacobians. And they can also be used to evaluate modular forms. More closely related to classical cryptography, we may see discrete logarithm problem pairing some particular kind of isogenies, like multiplication by L is an isogeny. Isogenies are used to transfer the discrete logarithm problem, so they can, if you can have some attack on some class of curves, you can try to attack a more general curve by transferring the DLP through isogenies, or conversely, they can reduce the impact of side channel attacks. And you can also use them for random self-reducibility in certain cases. That's worked by Benjamin here. And of course, more recent development of application of isogeny is everything based on isogeny-based cryptography. So it first started with the hash function of Gottschalk, Goren, Lauter, and it exploded with key exchange like SIDE, CSIDE, and signatures like SCASIGN. Okay. So what about higher dimensional isogenies? For cryptography, well, for classical cryptography, people mainly work with elliptic curve or a bit abelian surface or Jacobian of genus 2 curve. Some people work in dimension 3. And for isogeny-based cryptography, most people stay in dimension 1, as there are some proposals for hash functions in dimension 2, but mainly very low dimensions abelian variety. So for higher dimension abelian isogenies, for higher dimension abelian varieties, mainly for algorithmic number theory, and we don't expect them to be used for elliptic curve-based crypto system, or at least we did not expect them until this summer, where, as well known, side was broken using isogenies for higher dimensional abelian varieties. So this was quite unexpected, right? So how does it work? Well, what we discovered this summer is that there is a very powerful embedding lemma, which says that generally an n isogeny, so I'll define later what it means, but if you think about elliptic curve, an n isogeny is simply an isogeny with kernel of size n. So an n isogeny can always be embedded into an n prime isogeny at the cost of going in higher dimension. And this works for any n prime larger than n. So, of course, it would work for n prime divisible by n, because you simply compose your isogeny with another isogeny. So this would give you n prime divided by n. But what is quite unexpected is that it works for any n prime greater than n. So what you do is you have a small isogeny from A to B. You embed A into a larger dimensional abelian variety I prime. You have your big isogeny F, which go to B prime, and you project back to B and give you back F. So this brings considerable flexibility at the cost of going up in dimension. And explicitly, if you write n prime minus n as a sum of 4 square, and you take this big 8 by 8 matrix, which defines an isogeny in dimension 8G, and if I'm not mistaken in my matrix, this defines n prime isogeny. And we'll see later in the talk how we could check this. So as applications, so two thoughts about how this could be used to break acid side by going in dimension 2. And I also prove in the papers that even if you don't have the endomorphism ring of the starting curve inside, if you don't go to dimension 2 but 4 or 8, you can always also break side in polynomial time. And actually in quasi-linear pairs, endomorphism ring. Another recent application is that if you take any isogeny, you can always find a representation of this isogeny which allows it to be evaluated in polylogarithmic time. So simply what you do is you embed F into the big F with n prime power smooth. And power smooth isogenies can be evaluated a lot faster than standard isogeny. So for now, this is mostly theoretical because computing this efficient representation takes quasi-linear time. So it would be nice to get this representation faster and so evaluate an isogeny directly in polylogarithmic time, given its kernel. Okay, so the conclusion of this embedding lemma is as follows. Side is dead. Hopefully we'll get other methods for supersingular key exchange. And so how does this lemma works? It's based on work by Kani. So what Kani showed essentially is the following, is that if you take an isogeny from A to A1, an isogeny from A to A2, and you complete into any commutative diagram. So F1 is an N1 isogeny, F1 prime is an N1 prime isogeny, F2 is an N2 isogeny, F2 prime is an N2 prime isogeny. Then this matrix here is an N1 plus N2, N1 prime plus N2 prime isogeny. So can we use this lemma in the particular case where N1 prime is N2 and genus 1? So in this case, he calls this an isogeny diamond, and big F is an N isogeny where N is N1 plus N2. And it's very easy, it's trivial to extend Kani's lemma to higher dimension, which I did, but it's not, it's really trivial. And this is a marginal form of Kani's lemma, where we have different degree here and here. And what I'll explain in higher time is that we can compute n isogenies in greater dimension. With this kind of isogeny, we can still compute it. So with this more general commutative diagram, we could still be able to compute this kind of isogeny. And I explain what I mean by this type of isogeny. Okay, so I give a brief overview of algorithms for n isogenies. Essentially, all algorithms I know, of course, to get an algorithm, you need to specify the model you work with. So essentially, to represent an abelian variety, either it's a Jacobian of a curve, so it's quite nice because you can usually work directly on the curve rather than on the abelian variety, on the Jacobian. And those are possibilities to work with the theta model. So first, for the Jacobian model, there are various formula which give isogenies for elliptic curve. And there is variant by Coel from his PhD thesis, which give various formula when you are given equation of the kernel rather than a generator of the kernel. In higher dimension, and dimension 2, Richelieu describe two isogenies between Jacobian of genus 2 elliptic curve. And there were various generalizations, including Mestre, which describe two isogenies between Jacobian of elliptic curve in genus G. In dimension 2, there are more explicit formula for small degree isogenies. Ben extended this kind of formula for quartic genus 3 curve for two isogenies. And when I started my PhD, I tried the analog of Velu's formula for genus 2, but it did not work. And at the time, I could not understand why it did not work, but now I understand why, and I will explain it. And so in the Jacobian model, the more general version is from Leuven, which describe an algorithm in quasi-linear time to compute an isogeny given generator of its kernel. So Leuven describes the case G equal 2 in details, and Milieu extended it for G equal 3. The problem with the Jacobian model is that in dimension starting 4, an abelian variety is generally not a Jacobian. So this kind of algorithms are restricted to a small dimension. To get to higher dimension, we need to use a theta model. So in the theta model, you can have two isogenies, which are given by the duplication formula for theta functions. I think they date back from at least Freeman. I don't know when exactly, but they have been known for a long time. And Montfort, Quasumicon would give marginal product formula, which unfortunately we cannot quite use them algorithmically because they require access to theta constant of higher level. So after my failure of trying to do an analog of Velu's formula, I looked with David Liebig to working with theta coordinates. So the first thing we managed to compute are L-square isogenies, not directly L isogeny, but L-square isogenies in essentially O of L to the G, and we need to take L to the G, G plus 1 over 2, L's roots of some constant, explicit constant. So for Walter and Thomas, we did work on radical isogenies. If you remind you of something, it's exactly similar. Like any root we take correspond to different L-square isogenies. So it's pretty similar. Then with Cossé, we managed to compute L isogenies and not only L-square isogenies. And the situation was a bit strange. So sorry, it should be a congruent. So the timing was L to the G if L is congruent to 1 modulo 4, and L to the 2G if L is congruent to 3 modulo 4. I'll let you guess why we had these two conditions. Different conditions. And very recently, we managed with David Liebig to get an isogeny algorithm in time n to the G for any n isogeny in dimension G. So this is our paper in nth. So the first version was actually in n to the G log n, and we just recently discovered how to remove the log n factor. So this is quite nice. But a word of warning is that if you work with the theta model in dimension G, you will get 2 to the G or 4 to the G, depending exactly on the model you use, coordinates. So it has an exponential dependency with the dimension. So unfortunately, computing isogenies in dimension like 30 seems unreachable with theta model. So a few more work where isogeny from equation of the kernel, on cyclic isogenies using remultiplication, but there are still a lot of works to do for cyclic isogenies. Okay. So don't hesitate to ask me any question while I talk. I cannot hear the audience, but maybe the speaker can translate can give me the questions. And now I need to explain why we are looking at polarization for abelian varieties and polarized abelian varieties for isogenies. So it's easier to explain how it works over the complex number because an abelian variety over C is quite an explicit description. It's given by a quotient V over lambda, where V is a complex vector space of dimension G. So it's a linear data. Lambda is a Z lattice from 2G arithmetic data. And you need something more to get an abelian variety. So what I've described here is a torus, but not every torus is an abelian variety. You need a polarization to get an abelian variety. So more precisely, a lattice can be described by a parallel matrix omega. And in general, this parallel matrix omega only give a torus. So omega is described by V square coordinates. So the moduli space of torus is of dimension D square. But what happens is that if omega is in the Ziegel hyperhalf plane, which means that the imaginary part of omega is definitely positive, then you can associate to it what is called a principal polarization. And so the lattice corresponds to an abelian variety. And so the moduli space of an abelian variety is only of dimension G plus 1 over 2. And we see that when G equals 1, it's a particular case where this dimension coincides, so every torus has a polarization. So what is a polarization exactly? There are several equivalent ways to describe it from the complex point of view, and then we see several different ways from the algebraic point of view. So the first way is to see it as an Hermitian form, H, on our vector space V, with the condition that the imaginary part of H should have integer value on the lattice. Another equivalent description is via a symplectic form E on V, sorry, it should be V, where we simply use E is the imaginary part of H. Another equivalent description is via morphism from A, use the Hermitian map from A to its dual. So this is the map phi H associated to the polarization. And what is interesting from the point of view of algorithms is that a polarization corresponds to a divisor, or more precisely to the algebraic equivalence class of a divisor. And we see that divisor corresponds to equations and coordinates. So that's what we need for algorithms. Okay, so more precisely, so to work algorithmically with an abelian variety, we need a projective coordinates like U1, UM, and the point P will be represented by its coordinate. And as you all know, to get coordinates on an algebraic variety, coordinates are given by sections of divisor. So you take a divisor, you take global sections, and if your divisor is sufficiently nice, like very ample, you get enough coordinates to represent points on your variety. So when we have two equivalent divisors, D is isomorphic to D prime, they essentially give isomorphic coordinates, and we can define the pK group of any variety as divisor modulo linear equivalent. Here to describe polarization, I need an isomorphism which is a bit stronger, which are algebraic equivalents. So I won't describe it exactly, but essentially algebraic equivalence means that the two divisors are translate of each other. It's the case if D is ample. So what this means is that algebraic equivalence essentially means the same coordinate up to translation. And since an abelian variety we can translate, we can always translate back to 0. So we like to work with divisor up to algebraic equivalence. So the formal definition is that algebraic equivalence, so the group of divisor up to algebraic equivalence is the Néron-Sévry group. We take the pK group and quotient by the peak 0, which are the group of divisor algebraically equivalent to 0. And what is written small, you should not read it, just some more technical details that I won't mention at all, just to be rigorous. Okay, so what you should recall here is that we want to work with coordinates, and to work with coordinate up to translation, we work with divisor up to algebraic equivalence. So algebraically, the polarization lambda will be a divisor theta up to algebraic equivalence. And we have the same kind of alternative representation as over the complex case. So it also can be given as a morphism lambda from A to its dual. So it's a convenient way to represent a polarization as a morphism from A to its dual, simply by P ascended to the translate by theta of theta by P minus theta. This is a morphism as the theorem of the square, and this gives me the morphism associated to the polarization. Another more or less equivalent way to look at it is via a pairing on A. So in general, the value pairing is defined on A times A dual, but since the polarization is a morphism from A to A dual, we can have a pairing from A times A. So some properties of polarization. The polarization is non-degenerate if the morphism is an isogeny, and it is positive if it comes from an ample divisor. And the polarization is principal if this morphism is an isomorphism. So in the following, I will only deal with principally polarized abelian varieties. So as an example, so last time, so the pairing corresponds to the symplectic form in the complex case. In the complex case, where the symplectic form, the algebraic version of the symplectic form is the pairing. So in particular, in the complex setting, we have a polarization, which is given by, you can have a diagonal. And the symplectic form is always of the form 0, d minus d0, with d is equal to d1, d2, dg. The kernel of Ch is isomorphic to zg over dzg. And the conditions are as follows. So H is non-degenerate, means that all eigenvalues are different from 0. And H is positive if all eigenvalues are strictly positive. So, like I said, when we have a polarization, it means we have a divisor, and it means we have coordinates. And we can know the number of coordinates we have. Essentially, if we have theta principal polarization, then n times theta has n to the g projective coordinates. So if you only work with theta, we only have one coordinate, so it's not enough to represent a point. That if we work with we have 3 to the g coordinate, and it's enough to describe every point on our abelian variety. More precisely, we have a projective embedding. So working with a small multiple of theta is enough to get enough coordinates. And sometimes we can even work with 2 theta. So in summary, polarization corresponds to coordinates up to translation. There is a particular case where we have a principal polarization, which are Jacobians. So if C is a curve of generic G, so Jacobian by definition is a peak zero group. So it's birational to C to the symmetric power of G. And if you look at the locus of all degenerate divisor on C, inside Jac of C, it corresponds to, it's a divisor which corresponds to principal polarization. And the nice thing is that C completely determined by its Jacobian and the corresponding principal polarization. So it's more or less equivalent to work with the Jacobian on its principal polarization or to work directly with C. So you have an analytic description of the Jacobian in terms of the Abel-Jacobi map, but I'll skip this slide because I'm sure Ben will speak a lot more on this subject. And now I'd like to focus on the difference between elliptic curves and abelian varieties. So on elliptic curve, when you have a degree d, it's a divisor d, its degree is an integer, and use an isomorphism between the Néron-Severi group and z. So in particular, there is a unique principal polarization which corresponds to any divisor of degree 1, for instance, the divisor 0e. And so there is a canonical principal polarization, so there is a canonical isomorphism E is isomorphic to its dual via P maps to this divisor. And using this principal polarization, we recover the well-known coordinates. So gamma of 0e, we only have the constant 1. 2 times 0e recovers the coordinate 1x. So x is not quite enough to describe points on E, but it describes points on the common line. And when you look at 3 times 0, E, we require the Weierstrass coordinates X and Y, and we have the Weierstrass model of E. So that's why for elliptic curve, we can mostly forget about polarization. There's only one principal polarization. By contrast, on an abelian variety in higher dimension, the same abelian varieties, so I don't change the abelian variety, but I change the principal polarization, and depending on its polarization, it could be a product of elliptic curve or non-decomposable, which means the polarization is not a product, or it could be a Jacobian of an hyperelliptic curve, or it could be a Jacobian of a non-hyperelliptic curve, or it could even be not a Jacobian. So the same abelian variety, depending on its polarization, could have quite extremely different geometry. So that's why really when we work algorithmically with abelian varieties, we always work with equations, so we always work with polarization. In fact, I don't even know of a way to test if two polarized abelian varieties are isomorphic without their polarization, without testing essentially all their polarizations. So maybe there's a more clever way, but I don't know how to do that without testing all polarizations. Okay, so that was a quick primer on polarization. We'll see more about them by with Ben's talk tomorrow. And now I can finally start looking at isogenies. So in higher dimension, an isogeny between abelian variety is a morphism, which means that it's an algebraic map that is a group morphism. And you probably know that for elliptic curve, it suffices to check that f sends 0 to 0 to check that it respects the addition law. It still works for abelian varieties. So this is a morphism, and an isogeny is a morphism whose kernel is finite and f is surjective. By surjective, I mean surjective on the algebraic closure. Equivalently, it means that the dimension of A and B are the same and f is surjective, or that the dimension of A and B are the same and K of F is finite. So isogeny have nice property. They are divisible on the left and on the right. So that's a small exercise. And when you have an isogeny, you always have a dual isogeny that work on dual abelian variety. So the dual abelian variety of B is B dual is peak 0 of B. So it corresponds to divisors which are algebraically equivalent to 0. And essentially, the dual of Q, what we take the divisor representing Q, and we take its pullback, it will be in peak 0 of A. So this is the dual. And the dual behave as we will expect. So G circle F dual is G duals and F dual. Isogenies are closely linked to pairings. Essentially, when you have an isogeny of kernel K, you can look at its dual with kernel K dual, and K dual is indeed the dual of K. So you have a pairing from K to K dual to the roots of unity. And if you apply that to the isogeny of multiplication by L, you recover the well pairing from AL times the dual of AL to UL. And what is nice is that pairings and isogeny are compatible in every way you can think of. So if I have the pairing of F, I can put F on the argument on the left or F dual on the argument on the right. And lastly, so an abelian variety has not a canonical principal polarization, which means that A is not isomorphic to its dual, but it's always isomorphic to its B dual. So there is a canonical isomorphism. A dual dual is isomorphic to A, and so F dual dual is isomorphic to F. Okay. So why do we care about polarizations for isogeny? Well, for an algorithm description of an isogeny, so I look at F, an isogeny between A and B. So I want to find coordinates V1, Vm, coordinates on B, which will be given by section of some divisor dB on B. Then I want to find, to express my isogeny, I want to find the coordinate Ui, which are Vi composed on F. These are coordinates on A, and it's easy to see that they are section of the divisor dA, which is a pullback of dB. And what happens is that we can check that the degree of dA is the degree of F times the degree of dB. So in practice, our abelian variety is given by principal polarization. So it's induced by some divisor, principal divisor theta A. And we work, so in practice, we work not with theta, but by a small multiple m theta to have enough coordinates, like m is equal to 3 or 4. And so, since we want to find a model m theta b on B, So, and coordinate vi circ f. So what we want to do is we want to relate the pullback of theta b by f with a principal polarization theta a. Or more precisely, relate the pullback of m theta b with m theta a. Okay, because theta a or m theta a has small degree, the pullback will have a large degree, the degree is large. So the pullback won't be m theta a, but maybe you can relate it. So that's our definition. So an isogeny between principally polarized abelian varieties and n isogeny if the pullback of theta b is equal to n times, so it's algebraically equivalent to n times theta a. So that's the definition. It means that n times theta a will give us the divisor we are looking for to descend it to b. Okay, so n isogeny means it relates polarization. It does not give information about the kernel for now. It only relates the polarization. So this is a term I use in one of my articles, but I'm sure it's used by some other mathematicians. So I like this term because it emphasizes the fact that we are looking at links between polarization on B and the polarization on A. So if we translate this condition in terms of a morphism, so recall that the polarization is also a morphism from A to its dual, it means that the morphism corresponding to F, the pullback of theta P, is given by this formula. So I permute the term, and so I put this term here is the polarization given on F of P. So this pullback is given by this map here. So in other words, I can define the pullback of the polarization by this map, F then lambda B then F dual. So this is here, F lambda B F dual. And F is an n isogeny. When I do these maps, I get lambda R times n. Okay, that's an equivalent definition of an n isogeny. I do this map and I recover n times lambda A. So since lambda A is a principal polarization, it's an isomorphism, so I can define F tilde by this morphism. So it's a morphism from B to A. So I go like this, and this time I use lambda minus 1 to go like this. So this is F tilde. And the reformulation of this is that F is an n isogeny is equivalent to F tilde F is equal to n. So be careful that F tilde depends on my polarization here, even if the notation does not show it. It's also equivalent to F tilde is equal to n by using B duality. And what happened for elliptic curve is that an isogeny between elliptic curve is automatically an n isogeny where n is the degree of F. So I didn't precise, but here my n will always be prime to the characteristic, so that I only have separate isogenies. I don't want to deal with inseparable isogenies in this talk. So for elliptic curve, all these notions are more or less trivial because an isogeny is always an n isogeny. So that's why we don't really care about it. Now, you probably heard that when we look at isogeny between abelian varieties, we want to look at kernels that are isotropic for the well pairing. So why do we want to do that? It's because, so first, we have, because of the compatibility of pairing with isogenies, we also have compatibility of pairing with the contragradient isogeny. So essentially, what this means is that the pairing A lambda B, so F tilde is a contragradient isogeny for the well pairing too. So that's why it's a dual morphism for the well pairing. So this implies, this formula implies that if I have an n isogeny, the kernel of F has to be maximally isotropic in A of n for the well pairing. So that's a necessary condition. If I have my n isogeny, my kernel is isotropic maxima. And the nice thing is that the converse is true, is that if I take a kernel K in n, which is maximal isotropic, then the polarization n lambda A descends to a principal polarization on B. So every maximal isotropic kernel corresponds to a quotient that has a principal polarization. Okay, but here you need to be careful of the following subtlety. So if you look at an isogeny between principally polarized abelian variety, A and B, and here I don't know yet that it's an n isogeny. I only know that its kernel is maximal isotropic. So I know that n lambda A descends to principal polarization lambda prime B on B. But lambda prime B may be different from lambda B, the one we want, okay? Because on abelian varieties, there may be a lot of non-equivalent principal polarization. So to be an n isogeny, which is f tilde f equal to n, is a stronger condition than just being maximally isotropic. It ensures, so not only we are maximally isotropic, but it ensures that lambda f is compatible with lambda b, and not any principal polarization on B. It's the one we want. So equivalently, we can look at, we can check that an f is an n isogeny by looking at this equation on the with pairings. It's an alternative condition if you prefer to work with pairings and contragradient isogenies. Okay. So some property of contragradient isogenies. So by biduality, we also have biduality of contragradient. So f contragradient is equal to f. Composition behave as you expect. So J circ f tilde is f tilde circ J tilde. So in particular, if f is an n isogeny and G is a m isogeny, the composition is an nm isogeny. And conversely, if G circ f is an n isogeny and f is an m isogeny, then G is an n over m isogeny, and m divides n. And we can use that to prove that an n isogeny is always a composition of isogeny of Li isogeny with Li prime. So we can always decompose an n isogeny into L isogeny with L prime. So for Caniche lemma, we also need to work with products of abelian varieties and product polarizations. So if I have two principally polarized abelian varieties, so lambda A on A and lambda B on B, I can look at the morphism A times B to A dual times B dual, given by the product of the polarizations. That's what we call the product polarization, as the name implies. And it's easy to check that if I have F, a morphism from A times B to C times D, then F dual is A dual, B dual, C dual, D dual. So F tilde is A tilde, B tilde, C tilde, D tilde. And so using this property, you can check that the 8 by 8 matrix I gave at the beginning of the talk is indeed an n prime isogeny. So it's a small exercise to check that. Okay. One last technical slide before I go to algorithm. So once I have a principal polarization, there is a nice way to describe all other polarization, mainly that if I take any endomorphism, which is symmetric under this polarization, so that phi tilde is equal to phi, then composing phi with my polarization gives us a morphism from A to A dual, and we can check that it gives a new polarization. So this shows that the Néron-Sévry group, which was our polarization, the groups of polarization is isomorphic. So once you have a principal polarization, it's isomorphic to the endomorphic rings that are symmetric. So it's isomorphic to the symmetric endomorphism. And so we can define more general isogenies than just n isogenies. So when we have any symmetric endomorphism beta, we can define a beta isogeny as f tilde f is equal to beta. So in dimension 2, that's a way to compute isogeny with cyclic kernels. Okay. So as an example, if I take an abelian variety, which is a product, and I look at an endomorphism f given by A, B, C, D, then it's symmetric exactly when A tilde is A, B tilde is D, and B tilde is C, where B is a morphism from A to B. So this shows that the Néron-Sévry group of A times B is the Néron-Sévry group of A times the Néron-Sévry group of B times OM of AB. So that's why on the product of elliptic curve, for instance, you have a lot of polarizations. If you take two isogenous elliptic curve, you will have a lot of polarizations. So one needs to be careful to distinguish the type of an isogeny with the type of its kernel. So they are more or less the same for an L isogeny. So an L isogeny has always kernel of type Z over LZ to the G. But even for elliptic curves, we can have different type of kernel. For instance, an L square isogeny can have kernel Z over S square Z. So if the isogeny is cyclic, or it could be the isogeny of multiplication by L, which has kernel Z over LZ times Z over LZ. And in dimension 2, we have even more possibilities. So these are possibly all S square isogeny, but the type of the kernel is different. Conversely, if you take a beta symmetric endomorphism with norm N, with norm prime L, a beta isogeny will have a kernel, a cyclic kernel, but a beta isogeny will be different from beta conjugate isogeny. So even if the type of the kernel does not quite determine the type of the polarization we want to work with. So there are two distinct notions. Okay, so that was it for the theory. So now we'll try to look at more concrete details and algorithm. So what does an algorithm look like? Well, we have as input a kernel, which is maximal isotropic for say A of n, where P1, Pg generator of this kernel, and they are described by coordinates ui. So this coordinate will be given by section m theta a of my principal polarization, where m is going to be small, like 2, 3, or 4. And the output I want is the quotient A over k. And I also want coordinate on this quotient. So I know that nm theta a will descend to, so n theta a will descend to theta b. So nm theta a will descend to m theta b. And so I will get coordinates vi on m theta b. And I want to evaluate f of p, so q equal f of p with these coordinates. Okay, so generic algorithm will work as follows. I construct the divisor D, which is a pullback of m theta b on A. So I want to construct this divisor. Okay, so by construction, this is a divisor which is invariant by translation by K, and which is algebraically equivalent to, so it should be nm theta A. And by descent theory, the converse is true. So I will start with nm theta E, and I'll try to find a divisor invariant by translation, which is equivalent to it. Once I have this divisor, I need to construct the coordinate vi circ f. So these coordinates are section of D by construction, and since I compose with F, they are invariant by translation. And so a nice feature is that, conversely, if you take a section of D which is invariant by translation, one can prove that it's of this form. So this means that the coordinates on B corresponding to m theta b are exactly the coordinates on A corresponding to the pullback of m theta b, which are invariant by translation by our kernel. So once I have my divisor D, I find coordinates. Then among these coordinates, I try to find coordinates which are invariant by translation. This gives me my VI. And so once I have this coordinate, I can evaluate them on P. So VI of Q is VI circ F of P. So this is the general framework. So let's try this first for elliptic curves. So for elliptic curves, we have the two size coordinates. K maximum in E of n. So I want a divisor which is invariant by translation. So I simply take the trace of 3 times 0 E and they're all points of my kernel. So this is the divisor, and it's certainly invariant by K. So I know by theory that this divisor descends to 3 times 0 E prime on E prime, which is E over K. So my size coordinates are section of D, but they are of course not invariant by translation by K. But if I take the trace, so big X and big Y are the trace, they are by construction invariant, so they will descend to coordinate on E prime. And if you look at the polar divisor of this function, it's easy to check that they descend to the various size coordinates on E prime. And this is exactly Velu's formula up to a constant. So Velu normalize this formula so that on the formal groups it's a bit nicer looking. And so the cost of the formula is simply a sum. So it costs O of, it should be n here, O of n. And we can recover equations for E prime by working over the formal group law. So I won't explain this, but here I'm just explaining how to evaluate my coordinates using Velu's formula. So before I go to higher dimension, I want to revisit Velu's formula a bit. So recall that our divisor D is this one. It's a translate under K of 30E. And what you want to do is to construct section big U of D that are of the form V circ F. So equivalently, you want to construct section of the divisor which are invariant by translation. So if U is invariant by translation, its divisor is also invariant by translation. And so we might want to construct U by constructing a principal divisor invariant by translation, but you need to be careful that if you take a principal divisor invariant by translation, in general, the corresponding function is not invariant by translation. So that's a caveat. we can have a principal divisor invariant by translation, but the function itself is not invariant by translation. So there's a small lemma. So if E is invariant by translation, it's written as the form sum of AI, sum of Pi plus T, where T is in the kernel. And I can look at P0, which is the sum of EI, Pi. And it's not too hard to show that the function is invariant by translation exactly when P0 is in K. So when f of P0 is equal to 0. So I don't give I give a small proof. I don't go into details. So how can we use that? So for instance, we can take any point Q1, Q2 on our elliptic curve. I can take this divisor here, which is, so I want to take a divisor invariant by translation. So I take the sum of Q1 plus T. So I want a point which is in K. So I will take a point P0 which is in 0. So I need to add minus Q1 here, get Q1 minus Q1 equals 0. And to get a divisor of the grid 0, I need to do the same thing by subtracting some divisors. So I look at the divisor of this form. So I know by this lemma that the function corresponding to this divisor is invariant by translation, and it's not hard to construct, it's this function. So it's not completely obvious that this function is invariant by translation from the definition, but we can prove it using this lemma. Okay, so we know that f E is invariant by translation, and it's not hard to check that it descends to x minus f q1 over x minus f q2, where x is the Weierstrass coordinate on the quotient. And what we have just done here, when q2 is equal to 0, is to recover the formula from Costello-Ising and Rennes, which is used by the square root value algorithm. So that's an alternative way of recovering this formula, where we look at divisors. I thought it was a quite fun way to look at it. Okay, so now what we want to do is to try to do various formula in higher dimensions. So this time I have an abelian varieties with a principal polarization theta A. I have a kernel which is maximally isotropic, so I do the same thing. I take D, the translate of theta A under the point of my kernel. This is certainly divisor invariant by K, which will descend. If I have U, small u, a section, big U, which is the trace, is certainly invariant by K. So it's a section of big D invariant by K. So it certainly descends to a function on B equal A over K. So as I said, that was the first thing I did when I started my PhD, but unfortunately it doesn't work. So why doesn't it work? It's because D is equivalent, algebraically equivalent to n to the g m theta A. Okay, but when I descend D by my n isogeny, I will get polarization which is of type n to the g minus 1 m theta B. So it's indeed the polarization that descends, but it descends to a polarization which is too big. What I want is m theta B. I don't want n to the g minus 1 m theta B. So that's the problem with taking a trace. The trace works when g equal 1, because when g equal 1, this n disappears. But when g is greater than 1, the trace gives us coordinates which are of the group 2b, which correspond to a polarization which is too big, and then we won't be able to work with it. Okay, so that's a big problem. So how can we solve it? So what we can do instead of taking the trace is looking at nm theta A. So we know that nm theta A is algebraically equivalent to something that descends. So nm theta A is not invariant by K. So this divisor does not descend to B, but it is linearly equivalent to a divisor which does descend. Okay. So previously I could take the trace to define D. Now I don't quite know what is D here, but I know that it must exist by general theory. So I know there is a divisor invariant by translation of the form nm theta A plus some function, the divisor of some function G. And since D is invariant, this shows that the divisor of this function satisfies this property for any point T in my kernel. So our goal here will be to construct the divisor D, or equivalently to construct this function G. Okay, so what happens is that what I need to do is that I know that when I translate nm theta A by a point of my kernel, it's always linearly equivalent to nm theta A, so there always corresponds some function Jt such that the divisor corresponds to this. And what I hope is that I can find a function Jt that glue together to a global function G. So they need to satisfy some classical condition. But if I find my function Vt carefully, they will glue together to a big function G, which will allow us to define order divisor D that does descend. So one way to rewrite this classical condition is to introduce the notion of theta group. This is an idea due to Mumford. So I look at all the points T and the function Vt which have this property. There's a group law on this group, and the gluing condition can be reformulated as I want to find a section from K to my theta group. So this is a reformulation of my classical condition. And once I have G, I can construct my function D and look at trace of function on D. But actually, I can write directly on NM theta A, which means that using this isomorphism, the trace on D will correspond to this twisted trace on NM theta A. So what this means is that once I have my function Vt that glue together, if I take this trace here, this is a function that will be invariant under translation by K. So will descend to B. Okay, so it's a bit like Venus formula, except that before I could take Venus formula, it was trivial to take a D invariant, so the GT was simply the function identity, and I could take the trace. It was simply the constant. Now I need to find isomorphism explicitly, and then I need to take a twisted trace. Okay. So it's going to be, so I briefly describe ideas for this algorithm. So a general framework for an isogeny algorithm. So what we need to do is we want to find the function GT, so which has this divisor, and we want functions that glue together. So the gluing condition is rather annoying to check. Fortunately, in most cases, we can use symmetry. So if we take a symmetric divisor to represent theta A, we look for symmetric functions. And if any odd, there's only one symmetric function. So this means that they automatically glue together. So we don't need to check the gluing, that they glue together. When n is even, there are two symmetric functions. So here we need to be a bit more careful to take traces that glue together. So it's a bit more annoying. And actually, the duality between n odd and n even can already be seen on the Venus formula. If you take n even and you look at the Venus formula twisted by a sign here, you also get another isogeny formula that works. So a small, I don't know if you ever tested it, but it works. Okay, so now we found our functions. Now what I need to do is we want to generate section big U of my big polarization using function. What we can use here, that the multiplication map is surjective, essentially. So what people can prove is that using multiplication and translation, we can always generate all function on nm theta A using only function on m theta A. Okay, so it's not too hard to generate function on nm theta A. And then once I have them, I can look at my twisted trace of this function to construct coordinates on B. Okay, so here I describe a general method to evaluate coordinates on B. But then if you really want to describe B, it's not quite enough. You need more work to reconstruct the model on B you want. So if you want, you know that B is a Jacobian, you need to work a bit to acquire the curve. If you want a theta model, you need to work a bit to acquire coordinates that correspond to a theta model. Like when you have an isogeny between elliptic curves, you might want to get an isogeny between Weierstrass model or between Edward model or Montgomery model. And so just having coordinates may not be enough. You need to work a bit more to find the coordinates that correspond to our model. It's exactly the same for abelian varieties, but I won't have time to go into details on this step, which is quite important in practice and difficult. And in summary, all these algorithms, so we can make this general type of algorithm work as soon as we have an effective version of the theorem of the square. So the theorem of the square says that this divisor is principal, so corresponds to a divisor mu pq. So for those of you who know Perry's about elliptic curve, it's exactly the same mu pq as the Miller function for elliptic curve. So as soon, in theory, as soon as you have an effective version of the theorem of the square, you can use it to compute the additional law, compute pairings, and also compute isogenies. So the details depend on exactly what this effective version means, but you have in theory a general framework. So as I explained at the beginning, we can instantiate this framework with two models. So in the theta models, on the theta model, our coordinates will be given by theta functions. So analytically, our theta functions are given by this analytic formula. And the nice thing about the theta model is that it's universal. It works with Jacobian, products, elliptic curves, non-Jacobian, whatever you mean. The problem is that in dimension G, you will have 2 to the G or 4 to the G coordinates. And another problem is that it's not always rational. So there are two problems with theta model. So we know how to compute an isogeny in O to the N to the G. We have a general framework to compute more general beta isogenies, but in practice, the details are hard to get right. So to get an efficient algorithm, it's quite difficult. So in theory, it works. In practice, it does not quite work quite well. So there is a particular case when we can compute special isogeny, beta isogeny is the case of product isogeny. So for instance, if I look at the product polarization, which is N1, 0, 0, and 2, it simply means I look at the polarization on A to the power N1 and N2 times the polarization on B, rather than just, so when N1 is equal to N2, it's N isogeny, but I can look at different power on A and on B. And inside the general framework, we can still compute this kind of isogeny in time N1 to the G and 2 to the G, because it's easy to, this kind of real endomorphism it acts by A and B, so it's easy to compute this real endomorphism. So a fun fact, okay, no, I will skip this part. We can use modular form from theta function to find interesting modular locus, like in dimension 2, this modular function describes product of elliptic curve. In dimension 3, we describe the curve of product of in Jacobian of elliptic curve, and it gives a way to test if an abelian surface is split. So it's not quite the most efficient way, but it gives a way using modular form to test if an abelian surface is split. So let me skip this part. And now describe briefly how we can people compute isogenies in the Jacobian model. So I'm almost finished. So in the Jacobian model, what happens is that if you have a function on C, it induces a function on the Jacobians. Simply we evaluate it on, so if we evaluate it on the diverger by this formula. So G on sum of Ni pi is simply the product of V of pi to the Ni. And the nice thing is that we can almost build all function on JC by function on C. Well, so I need to add some determinants, but more or less the philosophy is that you can build functions on JC by working only on C. And so those of you who did some pairing computation on JC, these functions are already enough for pairing. So they are not quite enough for isogenies, but they are enough for pairing. So that's the nice thing about pairings for Jacobians. We can work with curve only with curve. And so, as I said, in the Jacobian model, the general framework I showed here has been used by Leuven Isogeny to compute isogeny between Jacobians. And it should not be too hard to extend this kind of algorithm to the product of Jacobians, essentially because if you have the term of the square on Jac of C1 and a Jac of C2, you have the term of the square explicit on the product. So it should be possible. I didn't do it yet, but there should not be too much difficulty. Okay, so to conclude, there are still a lot of open problems for isogenies between abelian varieties. Like we need better algorithms for beta isogenies. Like in practice, implementing them is a nightmare. The constants are huge. So I would like to improve that. In dimension 1, so value is in O of n, but you probably heard of the square root of t value formula, which is since O tilde of square root of n. It would be nice to also have an algorithm in O tilde of n to the g over 2 for general abelian variety. Another question would be like a batch isogeny evaluation, more compact model of abelian varieties, like if you want to compute isogenies in dimension 30 or even 100, you cannot use a theta model because there will be too many coordinates. So maybe is there a way to have more compact model? And of course, here I've just briefly described to evaluate an isogeny on a point, but it's only a small topic of a whole field of algorithms related to isogenies, a topic which involves modular polynomials, differential equations, and so on and so on. So it's only a small part of algorithms for isogenies between abelian varieties. And so there are still a lot of work to do, which is quite exciting. So thank you. I hope you were able to hear me and not hesitate to ask any questions.
So thanks a lot for this nice talk, and we could indeed hear you very well. So that the sound problem was resolved. We have time for a quick question, but I think we should then move to Benjamin's talk. Is there? I hope I didn't put. Yes, yeah.
Hi, Damien. So a couple of slides back, you talked about your general structure for using theta functions to compute. Yes, it's actually using the theta model, this one. And you're using your theta functions of level 2 and 4.
Yes.
Do you have any troubles with using this, for example, to compute 8-dimensional 2, 2, 2, 2, 2, 2, 2 isogenies? I don't know if there's enough twos, but you know what I mean.
Yes. So it should. So I wanted to do isogeny dimension 8 to give you some timings. I didn't have the time. So previously, like when I did explore isogeny graph in dimension 4, I did some 7 isogenies in dimension 4. And well, okay, so it's slow, but not that slow. It's like 1 minute or something like that. So in dimension 8, of course, we're going to lose a factor 2 to the 4 at least, and another 2 to the 4 because it's going to be like a 3 isogeny. We go from 3 to the 4 to, so when we go from dimension 4 to dimension 8, we go from 2 to the 4 coordinates to 2 to the 8 coordinates. And also the algorithm goes from, like, to compute an n isogeny, goes from n to the 4 to n to the 8. So if n is, say, 2, we are going to lose another 2 to the 4. So we lose at least 2 to the 8. So it's going to be at least 250 times slower than in dimension 4. So I expect it to be quite slow, but it should be doable. Like at least 1, 2 isogeny or 3 isogeny should be doable. But I did not have time to do it.
You don't have any problem with the degree not being co-prime to the level?
Yes. So yes. So we have a problem with yes. That's why your question. So not co-prime to the well, it's a bit more difficult, but we know to solve this in theory. But for 2 isogeny, it's just duplication formula. So this was already known. You just need to take the right sign. So the duplication formula is not your work, it's already known. But yes, it's a bit harder because, but it's, we have some, we know to do that. It's in my HDR thesis.
Thank you.
Okay, if there are no further questions, then let's thank Damien again